Right, guys, today we are going to discuss some past paper questions which is given under thermal physics, right? Okay, the first questions uh, is given, it was given at the 93 A levels, right? Okay, so it is can be considered as the third question in your past paper, right? Okay, and rigid gas at 27 Celsius is trapped in a vessel at atmospheric pressure by placing a light lid on the mouth of the vessel as shown. The area of cross section of the mouth of the vessel is 1 square centimeters and the atmospheric pressure is 1 into 10 to the power 5 Pascal. Right. So in the first question, the temperature of the gas in the vessel is raised while keeping the weight W on the lid to prevent gas escaping from the vessel. Find the minimum value of W required to keep the gas in the vessel at 27 Celsius, right? So now you know that, so this is the theory of this question, right? Uh, Now let's consider this one. You might familiar with this equation, isn't it? That is pressure equal to force over area, right? Then we can able to adjust this equation as F equal pressure into area, right? Then now let's consider this one. Let's assume that the air pressure above the lid as the P and the area of this surface as A, right? Then we can able to obtain an expression for the force exerted by this air column on the surface as, let's assume that the force as if not, then F naught can be obtained by using this equation, that is P equal F naught equal PA, right? Okay, so likewise, uh, we can able to obtain the force which is exerted by uh, from the pressure, right? Okay. Now, on the other hand, guys, this force is always exerted perpendicular to the surface, right? So pressure force, that's mean the force exerted due to the pressure is always exerted on the particular surface in perpendicular way, and keep in mind that, right? Okay. Now, if we consider the lid of this bottle, right? So you know that the pressure above the lid is can be considered as atmospheric pressure. Let's consider it as P naught, and let's assume that pressure inside the bottle or inside the vessel as P, right? So then um, now you can able to figure out the force exerted by the atmospheric pressure on this liquid. That is, as I mentioned earlier, this pressure is definitely exerted on the lid in a perpendicular way, which is exerted by the atmospheric pressure. So that pressure, that force, let's call it as F naught. So the F naught can be obtained as pressure, that is mean P naught into A, right? And this force is exerted on the liquid towards vertically downward direction. On the other hand, let's assume that the pressure inside the vessel as P, then the air which is inside the vessel is also exert a pressure force on this lid, and it is also exerted perpendicular way, right? So if we assume if we consider the force as F, then we can able to obtain an expression as F equal P into A. And so these are some basic theories, right? Okay. The other thing is this lid also having a weight. So we have to mark the weight also. Right. So the weight is given as W Now, guys, normally in some questions the mass can be given. So then, if it is, you have to convert the mass into weight, right? But in this question, they directly mention the weight of this liquid as W. So you have to consider the weight as the W, only the W, not as Wg, right? Okay. Now, this lead in equilibrium state under these forces, right? So there are three types of forces exerted on this lid, and what are they? First one is weight of the liquid, weight of the lid. The other one is force exerted by the atmospheric pressure, and the force exerted by the air inside the lid, right? So if we consider the equilibrium theorem, then we can able to obtain this equation F as F naught plus W equal to F, right? So I think you can able to figure out this equation, isn't it? But normally, if an object staying at a equilibrium state, the resultant forces exerted on the object is equal to zero, right? Then by considering that theorem, we can able to derive this expression, right? Okay, now then we can able to further substitute this obtained value for this equation. Then F naught can be written as P naught A plus W equal PA, right? So these are some simple things, right? Okay. Then, right. So at the beginning of this question, uh, they have mentioned that the temperature of the atmospheric air as 27 Celsius. If it is converting to Kelvin, that's obviously equal to 300 Kelvin. Then uh, the temperature inside the vessel is increased up to 127 Celsius, right? Then, now guys, you know that. So when you go through this question, you can able to figure out that volume might remain as constant, isn't it? Because there's no any clue regarding related with the volume. So then we have to consider that then volume should be remain at a constant value, right? So then you might have heard the pressure law, right? So this is the theory. In pressure law, in gases, we have learned that in a ideal fixed gas, when the volume is remain at a constant value, this equation can be used, right? Okay, so this is the theory behind this question. Now, if the pressure is equal to 1 into 10 to the power 5 at the 300 Kelvin. Now what will happen? What is happened here? The temperature inside the beaker is increased up to 400 Kelvin. Then we have to find the pressure inside this vessel at the 400 Kelvin Celsius, Kelvin temperature, right? To obtain that, we have to use this equation. So if I substitute this equation for this given value, then we can able to consider that 1 into 10 to the power 5 over 300 equal to P over 400. Then if we simplify it, then we can able to derive that P equals 4 over 3 into 10 to the power 5 Pascal, right? Because guys, now according to this question, now this lid is in equilibrium state, right? So then the pressure inside the obviously the pressure inside the vessel should be having a greater value than the atmospheric pressure, right? So this pressure can be obtained by using these equations, right? Then now we have already found the value for P, right? So let's substitute the obtained value for this equation. Here P naught is considered as the atmospheric pressure. So the atmospheric pressure is equal to 10 to the power 5. A means, now guys, this the area of the vessel is given as a square centimeter value. So how to convert the square centimeters into square meters by multiplying 10 to the power minus 4, right? So then we have to multiply the area is a 1 square centimeters. So in order to convert this value into square meters, we have to multiply this value from 10 to the power minus 4, right? Plus W equal P mean 4 over 3 into 10 to the power 5 into 1, but we have to convert it this value into square meters. So that's why I multiply this given value from 10 to the power minus 4, right? So let's further simplify this one. Then we can able to obtain that 10 plus W equal 40 over 3, right? So this is the answer. Then we can able to let's take this 10 into the opposite direction. So it is converted to negative. Then W equal 40 over 3 minus 10. So if we consider the common denominator as 3, then we can able to obtain an answer for the W as 10 over 3 Newton. So this is the value for W, right? In order to keeping the in order to prevent gas escaping from this vessel, right? Okay, now guys, just familiar with this pressure forces, right? Because normally these are some uh, these questions can be accepted at the exams, right? Okay, just you have definitely have to be familiar with these types of. Okay, let's move on to the second one. Now in the second part of this question, suppose a small quantity of water is present in the vessel at 27 Celsius. So first of all, what's that mean? Now this question is mentioning that there's a small quantity of water is present in the vessel at 27 Celsius. So that's mean, right? So just keep it N at atmospheric pressure. Find the corresponding minimum value of W, assuming that sum of water still remaining in the liquid from at 127 Celsius, right? And also it is mentioned that the saturated vapor pressure of water at 27 Celsius and 127 Celsius are blah 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 respectively, right? So guys, what's that mean? Remain water in 27 Celsius. So what's that sentence is referred for? Right. So in any questions, if they mentioning about this kind of things, that's mean now they are normally initially we are discussing about the only the gases, right? But in this instance, we have to be at consider that there's a gas plus vapor is inside this vessel, right? So that's why they have given uh, the saturated vapor pressures, right? So this should be identified by looking at the questions, right? That's mean in the 20 in this vessel it is consists of gas as well as vapors, right? So then now you know that guys, vapor can be divided into two parts. That is saturated vapors and unsaturated vapors. Then how to identify whether it is saturated? Saturated mean now if they mentioning about some amount of water remaining in the question, remaining in the vessel, or then we definitely have to come to a conclusion that okay, then the vapor which is inside this vessel is obviously become saturated. So that means saturated vapor is in the beaker or in the vessel at the 27 Celsius. And they also mentioned that there's another amount of water is present at the 127 Celsius too. So that's mean both these instances, that's mean 27 Celsius as well as the 127 Celsius, the vapor should be saturated. So the saturated vapor is in the beaker in the 27 Celsius as well as the 127 Celsius. So that's the meaning of this sentence, right? Okay. Then the other thing is, you know that we can able to apply the Boyle's gaseous law for the any kind of gas, right? Any kind of ideal gas. But when we come to the vapors, we can't able to apply the gaseous law for the saturated vapors, right? But even though we can able to apply the gaseous law like Boyle's law, pressure law, uh, Charles law, likewise we can able to apply for the unsaturated vapors, right? So the only the equation we can able to use for the saturated is PV equal nRT, right? So that's the only option for the saturated vapors. Okay. Now, but even though there are some exception, even there's an unsaturated vapor in a particular space, we do apply the equation for this kind of saturated vapors, right? But there are some special things to be noted. So I'm not going to discuss about those stuffs in these questions, right? So but keep in mind that, right? Okay, then now, at this, if there's a saturated vapor inside this vessel in both instances, we have to calculate the W to avoid the escaping gases from the vessel to the outside, right? Okay, so the same principle had to be used in this instance too. But even though uh, we have to consider the theoretical things which is learned in the vapors, right? Okay. Right. So guys, initially, uh, the air which is inside the pressure, inside the vessel is at atmospheric pressure, right? But what happened? The temperature inside this vessel is increased up to 127, right? This is increased up to 127. Now guys, uh, now, if the the pressure inside the vessel at the 27 Celsius is equal to 1 into 10 to the power 5 Pascal, mean the pressure, now you know that at the 27 Celsius there's a gas plus saturated vapor inside this vessel, right? Okay, then this should be, let's consider it as P total. So the P total is equal to pressure of the air, partial pressure of the air plus partial pressure of the saturated vapors, right? That's mean now they have given the saturated vapor pressure at the 27 Celsius as well as 127 Celsius. So the value is, so if the total uh, pressure is 10 to the power 5, then we don't have idea about the partial pressure of the air, but we do have idea about the saturated water pressure or vapor pressure at 27 Celsius. Right. So this is the value. Then P naught A equal to. So guys, I'm arranging this value also in order of 10 to the power 3. Then can be considered as 100 10 to the power 3 minus 2.7 into 10 to the power 3. Then the answer should be the 96.3 into 10 to the power 3 Pascal. So guys, this is the partial pressure of the air inside the vessel at the 27. So then what happened? The temperature inside the vessel is increased up to 127. So at the 127, let's consider the total pressure inside this vessel as PT dash, the PT dash equal to partial pressure of the air plus partial pressure of the saturated vapor, right? So at the 127 Celsius, the saturated vapor pressure have given. Then, if we have idea about the PA dash, then we can able to obtain the value for PT dash, right? Because now at the 127th, if we mark the forces which is acting on the lead, that is the pressure force which is generated by the atmospheric pressure, and the force which is generated by the pressure inside the total pressure inside the vessel, and the weight is also there. So if I rebuild the equation, we can able to consider that now even though these are pressures, right? So these are pressures. So in order to convert this pressure value into a force, we have to multiply from acceleration, right? So if we consider the equilibrium state of equilibrium state of the liquid, or the equilibrium state of the lead, then we can able to obtain an value for P dash TA equal P not A plus P not A dash plus W, right? So then first of all, we should have idea for PT dash, right? So guys, now you know that P not A, right? Now you know that as I mentioned earlier, we can't able to apply the gaseous law for the saturated vapor pressures. But even though we can able to apply this equation for the AR, no? So then we have idea about the partial pressure of the air at the 27 Celsius. So then by using the pressure law, that is P over T equal constant. By using this equation, we can able to obtain the partial pressure at the 127 Celsius, right? So let's go through this one. To obtain partial pressure of air at 127 Celsius, right? So now we are applying this equation for the AR, right? Then, so this is the equation T1 over T1 equal T2 over T2. This P1 mean this value, that is 6.3 into 10 to the power 3 over 300 equal PA dash over 400, right? So by simplifying this equation, we can able to obtain the value for P dash A, right? So finally, we can able to obtain a value for PA dash as 1.28 into 10 to the power 5. 1.28 into the power 5 Pascal, right? So see, so how many theories should we have to idea to solve the questions, right? So that's the thing that you need to obtain by doing these questions, right? Okay, then so that's mean the total pressure at the 127 should be equal to 1.28 into the power 5 plus. So what is the saturated pressure at the 127 Celsius? That is 2.5 into 10 to the power 5. 2.5 into 10 to the power 5. So then this is the total pressure at the 127 Celsius inside the vessel. Right. So this is the total pressure. So by using this value, we can able to obtain a value for W, right? So let's consider this equation as the A. Right. So if you substitute the values for the A equation, PP dash into A, that's mean 3.78 into 10 to the power 5. But we have to given this value as a force. So that's why we have to multiply it from the area of the lid. So it should be 1 into 10 to the power minus 4 plus, sorry, equal. Now here P naught A means the force which is exerted by the atmospheric air or atmospheric pressure. Then it can be considered obtained as 10 to the power 5 into 1 into 10 to the power minus 4 plus W. Then it should be 37.8. Then W equal 27.8 Newton. See, the weight of the lid is getting deferred at the two instances, right? So that's why the final conclusion is if there's a air plus vapor mixture, we have to apply the pressure of the gaseous law except the PV equal nRT for the gases only. But right, but when you do the when you perform the application for the gaseous law for the saturated vapors, we have to consider some important facts, right? Okay. So I think you have obtained a kind of idea about this question, right? Okay. In the third part of this question, state why water can remain in liquid form at 127, right? So guys, normally in atmospheric pressure, boiling point of water, boiling point of water is equal to 100 Celsius, right? And theoretically, we have learned that when the pressure increase, what happen? Boiling point also getting increased, right? When the pressure is increased, the boiling point is also getting increased. So the question is asking, so then if the boiling point of water is 100, then what the hell, which is water remain at a liquid form at the 127 Celsius. So the theory can be obtained by using this facts, right? So the issue is the pressure inside the vessel is greater than the atmospheric pressure. That's the first thing, right? It is obviously it's having a greater pressure inside the vessel than the outside, right? So the pressure is increased. What happened to the boiling point? It is also increased. So at this point, this is the pressure inside the vessel. So if we consider this value, it is obviously is greater than the atmospheric pressure. No? So then what happened? The boiling point when the pressure is increased, boiling point also getting increased. So that's why the water still remain at as a liquid, right? Okay. So in the fourth question, at 27 Celsius and at atmospheric pressure, if the vessel contain only air and saturated water vapor without any water in liquid form, right? What will be the final pressure inside the vessel at 127 Celsius if this value is differ from corresponding value in 2? Right. So guys, now just observe this calculation very carefully. According to the fourth question, at the 27 Celsius, atmospheric pressure, if uh, if the vessel contains only air and saturated water vapor without any water in liquid form, right? They directly mention that there's a gas plus saturated vapors, right? But even though there's no any amount of liquid or there's no any quantity of liquid which is bottom of this vessel, so that's sense. What's the meaning of this sentence? That's mean this vapor is saturated, is obviously saturated, but it is in a transition point, right? So now guys, you have learned that if there's a slightly saturated vapor, then what happened to the when the increase of temperature? When the temperature is increased, the vapor pressure is also getting increased, right? So if there's a slightly saturated vapor, with the temperature increase, it obviously the saturated vapors obviously convert into unsaturated vapor. See? Right. Just think about these graphs, right? You might remember these are some well-known graphs which is learned in the under the thermal dynamics, right? Okay. Right. So the question is asking about the what is the pressure at the 127 Celsius. So guys, now keep in mind that uh, we can able to directly apply for the equation, gaseous equation for the gases, but even though we can't able to apply the gaseous law for the saturated vapors, but but if it is a slightly saturated vapor and with the temperature increase, the slightly saturated vapor definitely convert into unsaturated vapors. So guys, by considering that point, we can able to apply the equation for the both gas and vapor at the same time, right? So you might have idea about this stuff, right? Then we can let's apply the this equation for the gases, gas plus vapor mixture, right? Then uh, and initially the value, the partial pressure of these two should be equal to 100 1 into 10 to the power 5 Pascal. Temperature is 30. When the temperature is increased, the pressure is also getting increased, but the saturated vapor, slightly saturated vapor is converting to unsaturated vapor with this temperature, right? So then, so the total pressure at the 127. Now I'm here, I'm considering P as the total pressure. That means gas plus vapor at 27 Celsius, right? So then, by simplifying this one, we can be able to obtain the value for this total pressure, right? So this should be the final pressure in this system, right? So I think you might get the at least a simple idea about simplifying these kind of questions, right? So just familiar with the Cash's law. Right. So then let's move on to the eighth question of this dude. That is, this question is given at the 1995 A-level exam, right? Okay. So before go to the questions, I want to tell you some theoretical things which is behind these questions, right? First of all, Lamai normally the pressure, air pressure can normally air pressure is given as a unit of Pascal or Newtons per square meters, right? But in some instances, we can able to uh, give the air pressure or any kind of pressure as the height of a mercury column, right? We can able to give the pressure as the height of a mercury column, right? So it is based on this equation, right? P equal H rho G. So if the rho and G are constant, then pressure is can be expressed as a height, right? Okay, now this is the first thing that I want to convince you. Then normally, if you ask to find the volume of a particular uniform shape object, then we can able to consider area into distance or the area into height, right? Okay. Um, the other thing, now let's take this kind of mercury column, right? Right. Let's assume that the pressure inside this space as P1 and the pressure of this space as P2, and let's consider the height of this mercury column as H. And keep in mind that this P1 and P2 values are given in the unit of mercury centimeter, right? So normally, if a pressure given as using this equation, that's mean the pressure is given as the height of a liquid column or the mercury column, right? Okay, now let's assume that all of these P1 and P2 both are given as a centimeter mercury value, right? Then the next thing is today. Now, as I mentioned earlier, if there's a pressure, this pressure is exerted a force perpendicular to the surface, and this pressure also create the pressure in a vertically upward direction, right? So now let's consider that this mercury column is tends to move downwards, isn't it? This mercury column is tends to move downwards. Then this mercury column is stay in equilibrium state by using these pressures, isn't it? So then we can able to consider that there are two types of pressures which is exerted downwards, that is P1, and we also can be considered as this H also as a it is also this mercury column is also tends to move vertically downwards. So then we can able to derive this kind of expression, right? Okay, let's take another one. Right. So if I ask you to obtain an expression between these three, let's consider the pressure at this point as P1 and pressure at inside this space as P2, right? So guys, now what is the relationship between these three? Now let's assume that P1 and P2 as are given as a height of a mercury column, right? So what should be the relationship? Definitely, this P1 is also exerted vertically downward. This P2 is creating pressure on the surface in vertically upward direction, right? So the thing is, we can able to derive an expression as P1 plus H as P2. So these are the some of the theoretical things which is behind this question. And keep in mind that we can able to apply Boyle's law. we can able to apply Boyle's law, that is P1 V1 equal constant. That's the meaning of Boyle's law. Right. And the important thing is when you apply the Boyle's law, you have to apply this equation for the same amount of fixed air column, right? Just keep in mind that. Okay, so these are some of the theoretical things which is essential when solving this question, right? Okay, now let's move on to the question directly, right? Okay, just turn the page number 5. Clearly identifying each symbols, write down the ideal gas equation. That's means that today PV equal nRT. That's the ideal gas equation, right? Then two identical glass bulbs A and B, each having a volume of 50 cubic centimeters, containing dry air, right? There's no any vapors. That's mean dry air at 227 Celsius are connected by a gas tube of length 100 centimeter and a cross-sectional area of 1 cubic centimeters. When the system is held horizontally, the 20 centimeter long mercury column contained in the tube is found to be at the middle of the tube as shown. When the system is held vertically, the top of the mercury column is found to be at the middle of the tube, right? So first of all, it's better to draw a relevant diagram. Draw a simple relevant diagram for these questions, right? So here, these are the two bulbs, right? And we have mentioned that the volume of a single bulb is equal to 50 square centimeters, and the area of this tube is equal to 1 square centimeters, right? So normally, guys, nowadays, if there's a question given as a format of this diagram, they normally mention that neglect the volume of this capillary tube or the neglect the volume of this tube, right? But in this question, we do have to consider the volume of this tube, right? Okay, then let's assume that this bulb as the A and this bulb as the B. Now, if this two bulb trees is in a horizontal plane, then we can able to consider that let's assume the pressure at this point as P1 and this one as P2. Guys, now the mercury column is located in the midpoint of this tube, isn't it? So that's mean the P1 should be equal to P2, or the pressure between these two values should be equal. Right? And let's consider this value as P. Okay, so this is the first thing that I want to know. Right? Okay. Then let's assume that the pressure at this point as P1 and the pressure at this point as P2. Let's assume that this is the bulb, this is the A bulb, and this is the B bulb, right? Okay. Now, so instead of P1 and P2, so from now onwards, I'm using the initial pressure of these two bulbs as P, right? Just keep in mind that this is this value as P and this one also as P, right? So then we have to obtain an expression by considering this pressure and the mercury column. Now, guys, the pressure inside this tube is P1 and the pressure inside this tube is P2, and the height of this mercury column is equal to 20 centimeters, right? So then we can able derive an expression as I mentioned earlier, P1 plus 20 equal to PT, so P2, right? Now let's assume that guys, these values are given as the height of a mercury column, right? So this is the equation that we can able to derive by looking at this diagram. Then we have to use the Boyle's equation too, right? We can able to use the Boyle's equation too, and keep in mind that if you apply the Boyle's law, it should be for the same fixed amount of gases, right? That's mean, and as an example, let's consider the this apply the Boyle's law for this instant and the or the for this bulb and the this one too. You can't able to apply the two different types of object of the Boyle's law, right? It is relevant to the other equations too, right? Okay, now let's consider the A bulb and we are going to apply this Boyle's law. That is PV equal constant, right? So the pressure at this A bulb in this position, we can able to consider it as P. We mean guys now the volume of this the bulb is 50 cubic centimeters. But even though we do have to consider the volume of this air which is trapped inside the tube, right? As I mentioned earlier, normally we can able to neglect the volume inside this tube, right? But in this question, we do have to consider it also. Then, what is the total volume of this instance? Now, if they mentioning about the area as the 1 square centimeters, and they have given the values of this air column too. That is obviously 30 centimeters, isn't it? It should be 30 centimeters. Then, sorry, this should be 40. This should be 40, right? Then, the volume of this part or volume of this air column can be considered as 50 plus 40, that means 90. Now, then let's consider the pressure and the volume at this instance. Now, this height should be definitely equal to 50, right? So the pressure can be considered as P1 and the volume of this space, this one 50 and this one also should be 50, right? So how does the volume is came as a 50? Because volume can be obtained by cross-sectional area into L. The cross-sectional area is equal to 1 square centimeters into L should be 50 centimeters. So the answer should be the 50 cubic centimeters, right? Then it should be 50, right? So it should be 50 plus 50, that is 100. Then we can able to derive an answer for the P1 as 290 over 10, right? Then right. Now let's consider let's apply the Boyle's equation for the B bulb, right? Then if you consider this at this point, pressure is at equal to P and the volume inside this A bulb plus the relevant tube is can be considered as 50 plus 40, that's mean 90. At this point, pressure should be equal to P1. So P2 volume should be 50 plus what is the volume of this part of the tube? It should be definitely 30, isn't it? Right. So guys, these are the values we can obtain for the P1 and P2. Let's substitute these values in the let's consider this equation and first one. Then P1 is equal to 9p over 10 plus 20 equal P2 mean 9p over 8. So let's take this one into the opposite side, then it should be equal to 9p over 8 minus 9p over 10. And let's consider common denominator as 40, then it should be right. So this should be the value. The first question is asking about the find the pressure inside the bulbs when the system is in horizontal position. So the question is asking about the P. Right. In the second part, in the vertical position, when the lower half of the system is maintained at a certain temperature T, uh, the mercury column moves up so that the bottom of the columns moves up so that the bottom of the column is in the middle of the tube. Right. So in this second part, now the temperature at this point is equal to 227 Celsius. And due to the temperature of the temperature in the lower half of the apparatus, what happened? Mercury column moves up so that the bottom of the column moves up so that the bottom of the column is at middle of the tube. Right. Then so at this point, this is the relevant position of the mercury column. Right? Isn't it? So now guys, let's assume that now initially we consider that pressure at these two bulbs as P1 and P2. Let's consider now at this instance, this is in converting to P3 and this one is equal to P4. Now, as we know that the temperature inside the lower part of the apparatus can be considered as T, right? Okay, now what is the expression that we can able to derive by looking at this diagram? That is P3 plus 20 equal P4, right? And now if we consider these two instances, we can able to consider that now at this point of volume of the of this considering space and the temperature have changed, and at the same time the pressure is also getting changed. Right. Uh, Now the temperature of the lower bulb is getting difference, and the temperature inside this bulb, or the uh, temperature inside the A bulb, the temperature of the A bulb remain constant, right? Okay, guys. Now, by considering B bulbs, let's apply this equation, that is P equal B constant, right? So that at this point, the pressure should be equal to P1 and volume should be 100, isn't it? In this instance, let's assume the pressure as P3 and the volume is can be considered as 50 plus this is 30, isn't it? There should be 8. Then P3 should be equal to P1 over 8. And now guys, now we have to remain the A bulb to apply the equation. So when you apply an equation for the A bulb, that is the lower bulb, what are the now the temperature, pressure, and the volume? All the things are getting changed, right? So the final conclusion is this is the only equation that we can able to use for the this B bulb, right? In this instance, here the P2 volume should be equal to 80 over 300. Here P4 into volume should be equal to 100. Temperature is equal to T. Now guys, do you know that we have obtained a value for P1 at the first part of this question, that is 10 over 8. Instead of P1, we can able to apply this equation, that is 9 we can able to consider substitute this as 9p over 10. That is the value for P3. But these are cancelled, and then it should be equal to 9p over 8. But we know that this is the value of the p, right? So let's substitute it. Right. So according to this expression, P3 is equal to 9p over 8. Now we do have idea about the p, that is 9 over 8. Instead of p, we can able to substitute that value. That is 4. That is 40 over 9. That's means these two is cancelled, and the P3 should be equal to 100, right? So if the P3 is 100, then we can able to obtain a value for P4. Let's consider this equation as a B equation. Now, according to the B equation, P3 plus P20 equal P4. Then value for P4 is 120 equal. Right. Now let's substitute the relevance value for this equation. Let's apply this so any value for the second equation. So P2, guys, previously we have obtained that P2 as these zeros can be cancelled on both sides. Then P2 into 8 over 300 equal P4 into 10 over T. Now we already have idea of the P4, but we don't have idea about the P2, isn't it? Then previously we have obtained that. In the guys, this values is relevant with the first part, right? So we previously we have obtained that at the first question we have obtained that P1 plus 20 equal to P2, right? Then right. So at the first question we have derived that P1 is equal to 9P over 10, right? Then we have obtained the value for P as 40 into 20 over 9. So these are cancelled. Then it is equal to 8. So if I substitute the values for this one equation, P1, if the P1 is equal to 28, then P2 should be equal to 100. Guys, keep in mind that I have used P1 and P2 at the first instance of this question, right? Then, if you substitute this value for this equation, then we can able to derive that 100 into 8 over 300 equal P4 into 10 over T. Then these can be cancelled. We already have obtained a value for P4, that is 120. Then T equal to T should be equal to 450 Kelvin, right? So that is the answer, right? So I know there's a huge simplification, but guys, now the thing is we have to learn by using this question is we should have a capability of deriving expressions by considering the pressures, and you should have a clear knowledge how to apply the Boyle's law or the pressure law for considering instances, right? Even though there's a little bit standard simplification, there's something in this question you should have to gain, right? Okay, right. Then let's move on to the ninth question in this tude. And this question is given in the 1996 LL questions, right? A cylindrical steam boiler made of a material of thermal conductivity 2.1 into 10 to the power 2, right? Thermal conductivity is equal to 2.1 into 10 to the power 2. Has a flat circular bottom of thickness 1 centimeter and cross-sectional area of 10 into the power 2 square centimeters. The bottom of the boiler is heated uniformly biogas burner. At the steady state, the boiler generates the steam at a rate of 40 grams per second. Heat loss to the surrounding can be neglected, right? Okay, now this area should be equal to 100 square centimeters, right? So now, guys, this question is based on the thermal conduction and the state conversion, right? So as you know that, what is the equation which is given a value for the rate of heat flow through a solid material? This is the equation, is it? Q over T equal Ka theta 1 minus theta 2 over L. So guys, this is the equation which is used to obtain the rate of heat flow through a conducting material in a steady state, right? And if you consider the state change of a material, this equation can be used. This is Q equal ml. But if I divide the both sides from T, then we can able to use this equation, right? And the other thing is, in a steady flow rate, we can able to equalize these two equations each other, right? So that's the another thing. The other thing is, guys, that you have given this value, that is 40 grams per second, right? 40 grams per second. So this is the rate of steam generate. It is equal to 40 gram per second, right? So when you're looking at this unit, it is equal to mass value divided from time. So this represent m over t, right? So keep in mind that. So the first question is, calculate the temperature of the flame of the burner, assuming that it is the same as the temperature of the outer surface of the bottom of the boiler, right? So now if they product the steam with 100 Celsius, then obviously the temperature inside the beaker should be equal to 100 Celsius. Let's assume that the outer temperature is theta. Now this is the direction of the heat flow, right? Okay. Now we have to use now, as I told you, at the steady flow rate, the rate of heat flow through this uh, bottom of the boiler should be equal to the rate of heat absorbed in order to convert uh, the steam generation, right? Okay, then so in the first question, they have given an additional data that the specific latent heat of vaporization of raw water, right? So let's use this equation, that is Q over T equal ml over T, right? So as I mentioned earlier, this m over T is represented this value, right? Then it can be considered as 40 gram per second. So in order to convert this value into gram, in order to convert this gram into kilogram, you have to multiply this given value from the 10 to the power minus 3, right? Then it should be substitute this L. That's L should be equal to 2.2 into 10 to the power 6, right? So guys, this is the rate of heat absorption for the steam generation, right? So then we can able to assume that, so this is the rate of heat flow through this bottom of the boiler tube, isn't it? Right? So then Let's use this equation for the boiler, the bottom of the boiler. Then Q over T plus QA, theta 1 minus theta 2 over L. Then the Q over T, or the rate of heat flow, definitely should be equal to this one, isn't it? Right? So then let's simplify this value. It is equal to 4 into 2.2 into 10 to the power 4, right? Then further it can be elaborated as this one, right? So this is the rate of heat flow to the bottom of the beaker or the boiler. Then this value equal to K mean 2.1 into 10 to the power 2 into A mean, guys, 100, but this value is given as a cube square centimeters. On order to convert square centimeters into square meters, we have to multiply this given value from the 10 to the power minus 4, and temperature difference should be theta minus 100 over this. L represents the 1 centimeter. So in order to convert this centimeter into meter, we have to multiply it from the 10 to the power minus 2, right? Okay. So when you simplify this equation, you can able to obtain that theta equal 523 Celsius. So this is the obtained value for theta. Now just be familiar with this kind of simplification, right? Because now you should have an idea by doing the questions how to simplify this equation at once, right? And what are the theories which is behind this question, right? Okay. Then in the second part of this question, after a long usage of boiler, a thin uniform material layer is formed on the inner surface of the bottom, and as a result, steam generation rate is reduced to 20 grams per second. If the thickness of the material layer is 0.1 centimeter, calculate its thermal conductivity. Right. So this is the just a rough diagrams after formation of the the layer inside the beaker, right? So as a result of this formation of this layer, is obviously is due to the deposition of the salt, right? So as a result of this deposition of this layer, the rate of heat steam generation is getting reduced, right? That's the thing that you need to highlight. Then when you apply this equation for the two types of different material, then you have to consider the temperature. So then you have to definitely apply this equation this each material separately. Now as an example, let's consider this equation. Let's consider this example. Now the temperature at this surface should be 100, right? Then you can able to figure out there's a junction between these two layers, isn't it? So then we have to consider the temperature as this layer as theta naught. And keep in mind, guys, the temperature in the outer surface definitely should be equal to 532 Celsius, isn't it? So I'm further elaborate these layers as A, B, and C. Just consider the AB as the original surface of the beaker, and BC layers is represent the newly formed layer inside the boiler, right? So then Likewise, so then we have to apply this equation separately. We have to apply an equation for AB as well as the BC. Even though now these surfaces are in a arranged according to series connection. So you should have an idea that the rate of heat flow through a seriously combined layers having a same value, right? So that's the next thing that you need to highlight, isn't it? Okay. Now, first of all, now they have mentioned that this is the rate of steam generation. So by using this value, we can able to obtain the rate. We can able to obtain a value for heat flowing rate through this material, right? So as I mentioned earlier, this m over t represent by this value. So let me substitute this one. So 20 should be converted now. This value is given as a gram per second. So definitely when you substituting the standard equation, you have to substitute in a SI unit, right? So that's the principle. Then I want to convert this value into kilogram per second. So this is the thing that I want to do when doing the conversion, right? And it should be equal to 2.2 10 to the power 6, right? So at the end, you can able to figure out that this value is equal to 4.44 into 10 to the power 3 watt, right? Okay. Then let's apply this equation for the AB surface. Then Q over T should be equal to 44 into 10 to the power 3. A mean is 2.1 into 10 to the power 2. A mean 10 square 100 square centimeters. That's in order to convert this meters, it should be have to multiply from 10 to the power minus 4. Then the temperature difference should be 500 theta 2 minus theta naught. Then 1 into 10 to the power minus 2. Right. So if I further simplify this equation, right. If I apply the equation for the BC surface, then the Q over T equal this one equal, we don't have idea about the K, and the area equal to the previous value, and the temperature difference should be substituted as theta naught minus 100 over 1.1 into 10 to the power minus 2. Right. So likewise, we can able to derive two expressions. So by simplifying these values, we can able to obtain the answer for the K, right? So the K should be equal to K should be equal to 21 watt per meter per Kelvin, right? So I'm not going to explain the how to make the simplification, but you know that, guys. Just just subject this value and subject this one also. Just add these to each other, right? So then we can able to obtain the answer for the K, right? Right. So in the third part of this question, suppose the steam boiler, after removing the above mentioned material layer, is to be converted into hot water generator. Hot water at 60 Celsius is to be taken out continuously from this boiler at a constant rate while feeding in cold water at 30 Celsius at the same rate. Calculate the maximum rate at which the hot water at 60 Celsius can be taken out from the boiler. Right. That's mean let's consider the temperature difference of the inlet and the outlet amount of water. Now, due to this, now this is the theory. Now the temperature of the outer surface is having a 532 value. So due to this heat burner, there's a heat flowing through this the bottom surface of the beaker, right? So by absorbing this heat, the cooled water is getting is increase the temperature up to 60, and it is moving outward from the boiler, right? So let's consider the water which is supplied to the beaker. So the theory is the temperature is up to 30 from 60, and the question is asking about calculate the maximum rate at which hot water at 60 Celsius can be taken out. Maximum rate, right? So that's mean they're asking about the M over T. Now guys, if there's a temperature difference, what is the equation that we can able to apply? It obviously Q equal mc theta, right? So there's if they're asking about the rate, then we have to divide the both sides from the T. See, at this point we can able to derive a term for M over T. So this is the thing that the question is asking for, right? So then Q over T equal M over T. C mean 4180. Theta mean guys, it should be temperature difference that is equal to 30. Oh, keep in mind that this theta is referred for temperature difference, right? Okay, now then let's come to the other part, that is this heat is given by the burner, right? And this heat flow is flowing through this bottom of the beaker, right? So then let's apply an equation for this case scenario, that is Q over T equal Ka theta 1 minus theta 2 over L. Now K is represented 2.1 into 10 to the power 2. A means 100 into 10 to the power minus 4. Now the temperature difference mean guys the temperature in the inner surface should be equal to 60, isn't it? Because the temperature which is moving outside from the moving towards the outside from this uh, hot water generator is 60. So the thing is, this is the temperature in the outer surface is equal to 532, and the inner surface should be equal to 60, right? Then the temperature difference should be 532 minus 60 over L mean thickness of the bottom of the surface, that is 1. In order to convert this value into meter, should be multiplied by 10 to the power minus 2. Right. So this both these equations given the same value, isn't it? So we can able to equalize these two equations to obtain a value for M over T. Right. So Now, when you go through these questions, you should have to identify what is the question which is asking in the what is the thing which is asking in the questions, right? And you should have a capability of applying these equations separately, right? Okay.